Okay, then we have a line currents, which is the currents in line conductors, and then we also have the phase currents, which is the current through phases. Okay, for the Y connection circuits, the V line is equal to Z3 times with the V phase. Okay, and then for the I line is equal to I phase. Okay, for a Y load, phase currents and line currents refer to the same thing, so that's why we get the phase current is equal to the line currents. Okay, and then we have a phase impedance. Okay, impedance from AN, BN, and CN. So we can look at this figure. So the impedance is actually from A to N, from C to N, and B to N. And then for a balanced loads, all phase impedance are the same. Okay, next we move to line and phase voltage for a Y circuit. Okay, for a balanced Y system, the magnitude of line-to-line voltage is Z3 times the magnitude of the phase voltage. Okay, each line-to-line voltage, okay, leads corresponding phase voltage by 30 degree. Okay, so the line-to-line voltage from a balance set, which is VAB equal to Z3 times VAN with the 30 degree. Okay, I will show you one example on how to calculate the line voltage by the given value of the phase voltage. Okay, for this example, the given phase voltage is VEN, which is equal to 120 volt with negative 45 degree. So the first question, we need to determine VAB, which is the line voltage from line A to B, using the previous equation. So look at this solution. Okay, so the previous equation given is VAB is equal to Z3 times VEN with 30 degree. So since we already have the value of VEN, which is 120 volt, so we just put into the equation. So Z3 times with the 120 volt with negative 45 degree times with 30 degree, and then we get 207.8 with negative 50 degree. So the next question, verify the line voltage VAB by direct substitution of VAN and VBN into equation VAB equal to VAN minus with VBN. Okay, so you need to verify the value for VAB, which is 207.8 with negative 15 degree, is equal with the phase voltage of VAN minus with the phase voltage of VBN. So we already have the value of VAN, which is 120 degree, 120 volt with negative 45 degree. Okay, but for the VBN, it has the same magnitude, which is 120 volt, but for the degree is negative 165. How we can get negative 165? Okay, since VAN is 120 degree apart from VBN, so for this one, negative 45 degree minus 120 degree, so we get negative 165 degree. So once we get the value of VBN, then we substitute the value in the equation given. So VEN minus VBN, so we get 207.8 with negative 15 degree. Okay, same with the first question. currents for a Y circuit. So in order to calculate the line's current, which is IA, IB or IC, so we use Ohm's law to calculate it. So figure A represent part of the load Y connection with the phase impedance, which is ZAN, ZBN and also ZCN. So for example, if we want to calculate the line's current IA, so IA is equal to VAN divided by ZAN, which is the phase voltage divided by the phase impedance. So we get the value of IA. Selecting a reference. Okay, before solving a three-phase problem, you need to select a reference. Normally for the Y circuit, we choose EAN or VAN. Summary of basic three-phase relationship. Okay, as I mentioned before, there are two types of connection for three-phase circuit. So we have a delta connection. Okay, sorry, this is grammar. Okay, grammar error. So we have a delta connection, a star connection. Okay, notice that there are a little bit difference between delta and star or Y connection. So for the delta connection, I line is equal to Z3 times with the I phase. But for the Y connection, I line is equal to I phase. Okay, we look at the V line. Okay, for the delta connection, V line is equal to V phase. But differently in the Y connection, V line is equal to Z3 times with the V phase. So this is the difference between delta connection and Y connection.